All right, so I know the end of that last podcast did go over the basics of these solubility curves, but I wanted to get all of these notes all together, cover the full page 6 here just in case you'd missed it or needed a refresher on it. So these solubility curves are some fancy graphs that have lots of lines, and those lines represent the maximum solubility level of these different substances at different temperatures. Remember that the maximum solubility is when our solution is saturated. So these lines represent where each different solution is saturated at different temperatures. So the most important thing to do anytime you're reading and getting used to a new graph is to look at our axes. So our y-axis is where our solubility is. That tells us how many grams of our solute will dissolve. And our x-axis is temperature. So at these different temperatures, how will our amount of solute dissolved change? Now, it's also important that we notice we've got different lines here. They're all going to have different solubilities. And like I said before, the lines represent where that substance is saturated. And then another really important thing to notice and remember is that this graph and most of these solubility charts are going to be based around 100 grams of water. And no matter what, they are going to tell you a specific amount of water. It is generally 100 grams, just kind of as a standard, because we have to tell you how much water we're working with, because if I had more water, then more stuff could dissolve, even at the same temperature. Less water, less stuff will dissolve in it. So every chart will tell you a very specific amount of water, and I think all of the ones that we're going to use are going to be based off 100 grams of water. So a lot of these questions will mention blah, 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 blah in 100 milliliters or 100 grams of water. And so once you see that, all that's telling you is that you can get your answer, get your numbers straight off of our graph. And while I'm talking about it, and I kind of just mentioned it, 100 grams of water is equal to the same exact thing as 100 milliliters of water, which is actually also exactly the same as 100 cubic centimeters of water. So as long as you've got 100 something of water, then we can read our numbers straight off of the graphs that I give you. Now, in our podcast, I did go ahead and go over these first 3 questions just to kind of introduce the simplest way that we can work through these graphs. And so here, as you see, question number 1 asks you for the solubility. That's going to be how many grams will dissolve of a saturated solution. So I'm going to be finding a line, finding where we're saturated for KNO3 at 10 degrees Celsius. So I need to come over here and find and focus on just the KNO3 line, and I like to kind of highlight it or trace it to help it stand out. And then I'm going to take my 10 degrees Celsius, and that's all that it gave me. But if I follow that all the way up to my line and then over to my y-axis where it tells me how much solute will dissolve, then that shows just, a little bit above 20. And I said that was about 21. If you think it's closer to 22, that's fine. I'm not going to split hairs over little digits there. This is not something we care about sig figs and precision with. If we need more precision, we're going to need better graphs. Another type of question that they could ask us would be to ask which compound is saturated. Basically, which line is there at 80 grams and 50 degrees Celsius. Notice it also says in 100 grams of water, but that just means that matches my chart, so I don't have to worry about that. I'm not going to be doing anything with this 100 grams number over here. All that matters is that I've got the same amount of water as my graph. So here I would just look at 80 on the y-axis, 50 on the x, and that lines up and hits our KNO3 line. And then finally, kind of similar to this last question, question number 3 asks us if we are saturated, unsaturated, or supersaturated, and it gives me the grams of my substance in 100 milliliters of water, so just normal, read it off of the graph, and 65 degrees Celsius. So once again, it's giving me my x and y axis numbers, so we're going to put those together, find where 140 and 65 are going to meet. And then we're going to compare that. I'm going to make that a little more visible. We're going to compare that to the sodium nitrate line. And the point, the data from our question, is above the line. And since the line represents where things are saturated, if I'm over saturated, then we call that super saturated. If my point, let's say that we only had like 100 grams dissolved at that same 65 degrees, because that's under my line, then I am under saturated. It would have to be exactly on that line if I wanted to be exactly saturated. So those are some of the simplest types of questions. And we're going to move on now to answer a few more different types of questions. And this next one asks us which solubility changes the least on this graph from 0 to 100 degrees. So we're looking for something that the y-axis, the solubility level, changes the least. And hopefully you can see it's kind of sneaky in here. This NaCl line almost blends in with that 40 gram line because it is just so flat. That definitely changes the least. The Ce2SO43 line is also pretty small compared to some of them, but that NaCl line is most definitely going to have the smallest change in solubility over the course of this graph. Now, question number 5 is a really important one to pay attention to because this is the first time as we read through it, we're seeing that we're going to be looking for a temperature. That seems a lot like the first problem we worked out. If my solution has 40 grams of KNO3 in 50 grams of water. So what I realized suddenly, and my mind's freaking out, I don't have the same amount of water as what my graph is made out of. So I can't just take my numbers, my answers off of the graph and be done with them. It doesn't mean that I can't use my graph. It just means I'm going to have to do some work, change my numbers a little bit in order to be able to use that graph. But basically, if I'm talking about this solution that is 40 grams in 50 milliliters or grams of H2O, and if I need my information to be about 100 grams of H2O, well, I could make my solution twice as big, and now instead of having 50 grams of water, I would have 100 grams of water. But if I have twice as much of this solution, then I can't just double the water. If I double the amount of water, and I want to be talking about the same kind of solution, that means I'm also going to have to double the amount of my solute. So what I should be looking at on the graph is our 80 grams of our solute, 80 on our y-axis, and following that over to our KNO3 line, and then down, and if we do that, it hits almost exactly here at our 50 degrees Celsius. So that is our answer. 50 degrees Celsius is when 40 grams of potassium nitrate would dissolve in 50 grams of water. So just remember that we always need to make the amount of water match our graph, and we're going to be putting those grams on there. And if I change my amount of water, I've got to change those grams of solute as well. Both of those are going to change together. Same direction by the same amount. Now, these last two questions are also kind of a little different and special. And so here in this question number 6, this is talking about KCl. So finding that line and highlighting it in 100 grams of water. So thank goodness I don't have to do any crazy math here. You might notice, and I don't know how much I've said this already, but I tend to scratch out or even just a single line. I want to visually keep myself from accidentally trying to look at that 100 grams on my y-axis. I see students do this all the time, especially if I see like 100 grams sitting right here at the end of a sentence, and I just see that, and I just go into autopilot. These graphs are so easy to read. I'm looking at 100 grams, and all of these temperature stuff and doing stuff with it. But once I see 100 grams of water, all that tells me is that I can read numbers straight off of my graph without having to multiply or divide by 2 like what we did last time. So I tend to kind of scratch that out so that I don't have to worry about it and I don't get confused and accidentally try and use that number. So after we ignore that, this evidently tells us that we are taking our solution that's saturated at 100 degrees Celsius and cooling it down to 20 degrees Celsius. And evidently when we do that, some stuff is going to recrystallize. And if you don't know, recrystallize, just like repeat, you did something once and now you're going to do it again. So crystallizing is forming crystals, and we say recrystallizing because when we make a solution, we take those crystals and we dissolve them. So they're not crystals anymore, they're dissolved in a clear solution. And so recrystallize is what happens when they come back out of the solution. They come undissolved from that liquid. So evidently there's going to be more stuff dissolved in the solution than will fit. We're going to be oversaturated, and so that stuff that's over and above, that extra stuff, is going to recrystallize. So let's get some numbers to work with here, because all that's really different than that first problem when it gave us 1 temperature and asked us for the solubility, here when it gives us 2 temperatures, we're going to use both of them and just read 2 numbers off of this graph, 100 and at 20 degrees. And I think at 100 degrees, it's a little bit more than halfway between 50 and 60. So I think I'm going to call that 56 grams. And I'm just going to make a note. That's at 100 degrees Celsius. And down at 20 degrees Celsius, it's a little bit more than 30. Definitely not halfway, though. So maybe like 31. You might think it's 32, and that's fine with me if you say that. This doesn't have to be perfectly inexact, as long as I see you clearly realize that was above 30 and less than 35. So this is what it was saying, is that at that higher temperature, I can and did evidently dissolve 56 grams until my solution was fully saturated. And then when I cooled it down, it could only keep dissolved 31 grams. That was where it was saturated at that lower temperature. And so the difference between how much I put in and that was dissolved at the higher temperature as compared to this lower temperature is going to tell me how much stuff doesn't fit anymore, how much stuff had to come out and recrystallize. So just like I just said the word difference, hopefully your brain is telling you that all we've got to do here is subtract these numbers. 56 minus 31 is going to be 25 grams. So that's how much will recrystallize or become crystals again after we lower that temperature. And this is that idea. If you were in class or if you want to Google it, Google recrystallize or supersaturated solution or there's so many cool videos I can show you, but this is what I was showing you with that sodium acetate recrystallizing and precipitating out, just because it's so cool, and we can figure out how much will recrystallize based on these graphs. Okay, so last question that we have to do as a group. Actually, there's one more that I'm going to touch on in a moment after we answer this number 7. And number 7 might seem a lot like number 5, but don't get too ahead of yourself. We're not actually going to be doing quite the same thing here. So this one is asking us how much sodium nitrate. So sodium nitrate is this NaNO3 line here. It must be added to make a saturated solution in 50 grams of water at 10 degrees Celsius. So some of you might be thinking, oh right, 50 grams of water, I need to multiply that by 2 in order to be able to look at my numbers on my graph. But when I double my amount of water and look at my graph, my temperature should not be doubling. Just like if I took 2 beakers of water and poured them together into a third beaker, I would have twice as much water, but the temperature of the water would be exactly the same. As long as I started off the same separately, just room temperature water, my water's temperature doesn't double just because the amount of my water doubles. If I did have 5 grams of salt dissolved here and 5 grams dissolved there, then I would have twice as much in that final solution. The grams, the mass of water and the mass of stuff dissolved would double when the water doubled. And that's because mass is extensive. And if you remember, we talked about that at the beginning of the year. It changes when the amount of matter present changes. But temperature was what we called intensive, means it was independent of amount. It does not change when all I change is how much stuff I've got. So you are never, ever, ever going to multiply any of your temperatures. You're not going to divide any of your temperatures. We are going to have to make some changes and do some special stuff because of this weird amount of water, but we're not going to be doing it right now because we don't have any numbers for stuff that would be changing here. So for right now, we're going to notice and make a note to ourselves that we have to do something about this weird amount of water. But for right now, all we need to do is start looking at that 10 degrees Celsius and following that all the way up to that NaNO3 line, and that will tell me my solubility. But I need to remember that that is telling me there that 80 grams of my solute will dissolve in 100 grams of water, because I was pulling that 80 number off of my chart where I have 100 grams of water. So now that I'm pulling it back to try and answer this question number 7, I don't want 100 grams of water. I'm dealing with 50 grams. So now that I have grams of my solute after reading my number off of the table, I'm bringing that back over to try and answer my question about 50 grams of water, which means now in order to take that number and answer my 50 grams of water question, I would have to divide my water by 2, which means that I'm also going to be doing the same thing with my grams here. So my final answer is that 40 grams of my sodium nitrate would dissolve if I had 50 grams of water. And it really throws some people off that even though question 5 and question 7 are both talking about 50 grams of water, in one we were multiplying by 2 and one we were dividing by 2. But the difference is whether we were starting off with grams given to us. If so, with my weird amount of water, I can instantly change that and make my water match and then just use my chart like normal. But here, when I have my weird amount of water with a temperature, we don't change the temperature. We have to go find the grams first and then change that number from the chart to match my question, instead of changing my question numbers to match the chart. So, I know it's a little bit weird. The best thing that we can do at this point, though, is practice. So, like I said, I do have one more quick question to ask you down at the bottom, and it's kind of more related to the stuff that's at the top of the page here, where we said that temperature and solubility of solids and gases. We talked about in class how our solubility of solids will increase. Heating up our tea helps our sugar dissolve faster, but the solubility of our gases actually decreases as the temperature increases. Like a soda is more flat. It has less dissolved carbon dioxide when it's warm soda, as opposed to when you pull it straight out of the fridge. So that solubility of gases is actually going to be the opposite of our solids in every case. So that agitation stirring a soda makes more of those bubbles come out, and it makes it less fizzy overall, less gases dissolved. So that's the big idea here at the top of the page that we need to make sure that we fill in. But my question for you, based on that idea, is can we tell which lines on the graph represent gases just from that simple fact? Hopefully, if you think about it, if we're saying that our gas's solubility, meaning our y-axis, is going to be decreasing as temperature increases, that means that as I go to the right, my y-axis value should be going down, aka they should have negative slopes. So if you look at that chart, there should be two substances on there that have negative slopes, and that's NH3 and Ce2SO43. So you might make a quick note that these are gases because they have negative slopes, either at the top by where we wrote these notes about the gas solubility being weird and opposite, or right there by the graph, or even at the bottom where you might have a little bit of space. But this is a really important idea, and I kind of set stuff up to talk about it there at the top, but never had a question about it later on. So just FYI, maybe it'll be important for you to know later on a test or a quiz. Hint, hint. So at this point in class, I gave people about 10 minutes to work on worksheet 10B, and I did post a second version of the solubility curve there. It's in our module underneath today's date, or the date that we took these notes together, called Solubility Curve from page 7, easier to read. Because I realized my printed copy was okay, but when we made copies of that copy, these numbers especially got real fuzzy and hard to read, and the intersections where things happen got a little bit fuzzy. So I would highly recommend that you come on Canvas and use this version of the chart so that you don't make any little silly mistakes as you are working on worksheet 10B. But if you have any questions about anything with this graph or chart idea, please come in and let me know, because it really shouldn't be the hardest part of this unit, but there are a lot of different things to keep in mind when you're answering these questions. So let me know how I can help.